Now we're looking at the graph for cosecant. We've seen the graph for secant earlier, and we're getting to the graph for cosecant. So before I show the graph here, there's a couple of things here. So when you have the input value, x, the angle, and then calculating cosecant. Once again, get these fast. Okay. What happens when we have x equals 0? What's the cosecant value for this? Again, cosecant is defined as 1 over sine of x. Okay. So when x is equal to 0, cosecant of 0 is it's undefined. Because, yes, sine is 0 at that point, right? And so we got undefined here. 1 over sine of 0. And sine of 0 is equal to 0. That's why it's undefined. Okay. What about the pi over here? It's another undefined. Right? Because this is the same as 1 over sine of pi. And yes, sine of pi itself here is 0. Agree with that? Then check to see if you guys agree with me. I say when x is equal to 2 pi, it's another undefined thing. Make sure you double check too. Do you agree? So how about a pi over 2 here? Okay. What's cosine? What's cosecant of pi over 2? You can think of that as 1 over sine of pi over 2. Right? Thank you. So now what about 3 pi over 2 cosecant of 3 pi over 2? Negative 1. I agree. Okay. And so just a few of these points are good enough, right? Now I'm going to put it on screen over here. Right, so here's our blank empty space. Right here, I'm going to slide a slider there, right? So that you can see the behavior of it. We got a few undefined points. So right at the see when x equals 0, which is right aligning with that vertical y-axis, right? We should be expecting a vertical asymptote over here, according to the table of values. At pi, we are expecting another vertical asymptote. And then at 2 pi, we are expecting another one just like that, because these are, according to our table of values, we've got undefined right at these 3 values again. And you have seen that the work earlier when we were doing cotangent, when we were doing tangent, and even cosecant, and even secant earlier. Right? Anytime that we have an undefined, and we end up with a vertical asymptote. And so now let's really draw the graph. So the graph happens like this. And let me put the vertical asymptotes in. See. So the vertical asymptote really happens at those places. So now the graph goes like this. Right? You see how it drops down from the beginning like that? From the beginning it drops down, right? And then it drops down, but only hits to a certain low right there. So the low it hits is a 1 right here. And then it's going to swing back up, trying to be asymptotic to that other second vertical asymptote right there. And we're going to continue. Right? And so now this time it's going to jump. It's going to make another jump, right, to the other piece again. And so now in the end, once you complete one cycle from 0 angle to the angle 2 pi, right, one complete cycle of your the unit circle rotation right there, and we have this shape of the graph. Yeah. See what I mean? Okay. So we have see, and it's one complete circle. I mean, the circle's angle goes from 0 to 2 pi. Right? So one complete rotation right here on the unit circle gives you, see, half the circle from 0 to pi gives you that upside parabolic shape, right? And then it's asymptotic to the 2 sides here. And then it switches to another exact, symmetric to this. Look kind of symmetric, but pointing down, right? And then again, similar to the secant graph that you have seen earlier. Looks like there's a little empty space at none of your graph. It's interfering with that. And right now, I'm only showing one basic unit of your cosecant here. But now we put in the actual graph here. Okay. For the complete. See, the idea of a trig function now is that once you can get one basic units done, right, the rest is going to come out just the same here. Now let me show the rest of them. The rest of them is just the replication, right? The infinite replication of those right here. So our basic unit is the one right here, see in blue, okay? And then the rest of that, you see, you can recognize these one right here, another basic unit right there, asymptote, vertical asymptote here, vertical asymptote here, and another repeat of that, and another repeat of that. Right? So we have an infinite number of repeats of that basic units in blue over here. Right? And then from the left here, see, we have those repeated ones starting out all the way from whatever negative infinity, right, up to our basic one through here. So now I'm going to hide away these things. Right? And let's have a closer look. All right, so when you're looking at this graphic here, what we notice, right, for one basic unit, we got it has a center line again, just like that, what you're seeing right in front of you. Got a center line. For this specific function that you're seeing right there, where's the center line at? The horizontal center line. Y equals 0, right? So right now for this graph is y equals 0, but once again nailed down the feature for this cosecant graph, it's got to have a center line again, right? That's all with that like that. Okay. And then so back into what caught my attention is right around that center line, one piece of the graph is doing this, and the other piece is doing that. So that's the major feature of your graph, right? And it has some empty space, and we'll get into that, right? There's an amount of empty space, and the empty space being some amount of vertical distance that swings away, right, from the center line. See what I mean? Okay. So I'm going to call that empty space. This is sort of a substitute for, an equivalent substitute for the amplitude. So we don't have the amplitude concept in secant and cosecant, but we have what's so-called empty space. Empty space, yeah. And so being 1, right? Because that's what we saw right there throughout the graph. Yeah. And this is the amount of space that swings up and swings down, right, from our center line. Okay. The empty space around the center line. Right. So any cosecant graph has that feature right there. If we want to nail it down. And then for this cosecant graph here, what's the total period window that you're seeing right now in front of you, from the picture? It starts as a 0, right? See, right now it starts as a 0 on the screen here, and then the last one that completes the picture of the one basic unit stops at 2 pi, right? Or it's ending at 2 pi. So the entire total window here, the total interval right there that takes one complete basic unit of our graph, right? That's 2 pi period. Now we're going to record that down. So period for this standard or ordinary cosecant graph, right? 2 pi. Are you all agree still? Okay. So it's another feature that was our attention, right? That we always want to pay attention to anytime we're looking at cosecant graph. And so for this particular graph, there's a starting point, right? And it's also another main feature with cosecant graph. For this function right here, starting point at 0, but then the main feature here is the starting point appears to be a vertical asymptote. And you guys should pick up this VA notation, right, from your previous course, right? VA stands for the vertical asymptote. Okay? So we're starting our graph with a vertical asymptote, and the graph happens in between the asymptotes, right? And then yes, that starts of our basic units, and then the ending of our basic units at x equals 2 pi, right? It's another vertical asymptote, right? So the way we get to that is, once again, permanent rule. The end is always the start, right? Plus the period window, and the length of your period. You got that. Check mark to that. So those we put the check mark on. I might have not done this with the other graph, but my intention is that these are the main features, right? The major features of which any of our trig graphs, so that we should always pay attention to. You know what I mean? Okay. And you can see that the empty space being indicated here, we recorded that down from our graph, right? But the empty space we're seeing here from this picture. And I want you guys to also consult with that table of values that we have. Let me one more time swing back to this. I hope you can see my mouse cursor motion over here. At x equals pi over 2, right? See, it hits a point being a 1. So this picture right here is particularly, is precisely consistent with our table values on right that you guys constructed for me, right? Before we got that. And then see it stays so that it looks like it's the lowest. It can go right on this area of our graph right there, and everything else is above that. And then there's at 3 pi over 2, we have another point right there. See where the little mouse cursor is pointing at, right? Okay, so in this area between the two vertical asymptotes there, then that point there where the mouse cursor is at is the highest it can go. And that's why it leaves a space between, right? And that space right there is, see, the one below the horizontal axis, and then another one above, right? That horizontal center line, right? And so, in that way, that clear this out a little bit. Yeah, just want to get you guys comfortable with that. We're gonna do a little bit of drill right here. To get the picture really nailed down in your mind, right? About the graph of the cosecant. But all you need is center line. Doesn't have to worry about x0 or what, right? But it's always gonna have a center line. You know what I mean? So you draw a center line, right? In some cases it's the x-axis, some other cases maybe a little bit up, some other cases a little bit down, but any cosecant graph has a center line. Sound good? And then away from that center line, there's an empty space, right? So like an equal distance empty space around it. See what I mean? Right? And then we pick the major idea is we pick a start. Right? The start is here, the ending is here. That total length of there is our period of the whole graph, right? And then we got a halfway point. So vertical asymptote happens right at those points there. Right? Start, vertical asymptote. The end is at the vertical asymptote. And also the halfway point is also a vertical asymptote. See what I mean? Okay. And now with the quarters, right? Look and consult right in the picture that you're seeing right in front of you. Those quarter points right there. We have, you see, one piece is a parabolic shape, pointing up, like a cup shape, right? Pointing up, being asymptotic to the two. The first two, in that space between the first two vertical asymptotes, right? And it hits to only as low as 1, right? Or as low as whatever that vertical, that empty space is twinning out again. Sounds good? And then the other part, the third quarter, see, another cut, but this time pointing down and being asymptotic between the two. That's how we're drawing it. You see, there's a certain order of my hand motion when I drew it, right? And I completely ignore how. Does it have to be a 0? It doesn't always. The point is, it's a start. Okay? You got a start. Okay? You got an end here. You know what I mean? Okay? And then you got halfway point there, right? And this line right here itself, I've been calling that it's a center line. That's how it happens. See what I'm saying there? Right? And then later on, when we get a little more intense into doing the problem, then there could be time that's on your center line, right? It starts, end, and depending for the cosecant, then your graph may go like this. And the empty space between right here, your graph may flip upside down, right? The two pieces may flip upside down if you can't, right? So we may have a negative coefficient that multiplies with our cosecant, resulting in flipping upside down right around the center line. That's another choice, right? That's another possible scenario that happens to our graph of the cosecant. One brief look back at the secant last time. So that's what we've had there was a cosecant. This is what the secant from last time looks like, from last lecture. We got center line, right? That's all we need. Center line. Secant is indeed the start, and well, we will always have an empty space, some empty space, right, around the center line. Next another one. So that's for. But then for secant, there's only one vertical asymptote. There are only two vertical asymptotes. It happens at the quarters. First quarter, third quarter, we place a vertical asymptote. That's making it different with the secant, with the cosecant we just now drew, right? I'm about to make the picture of the secant graph from last lecture again. So starting point, we got that point right here, asymptotically going up, right? And then the ending point, right? That's secant. And then halfway point right here is that sag roundy face there, right? Pointing down. Okay. So that's secant. Only two vertical asymptotes. Right? They start and they start at that point, right? And this line right here is a center line, right? Okay. And vertical asymptotes at quarter, right? First quarter, third quarter. You guys see the difference? Right. All right. Then just right over there on that other board, we just now in this lecture we learned about the cosecant. Good so far? Okay. So there's some other minor information, but it will become useful later on. So secant itself, right? Secant itself is an even function. So see, that means when you're substituting in a negative input for secant, and it will come out being exactly equal to just the ordinary secant. Okay? This property will become useful because secant is even. Okay. Well, graphically you can see it like this. Center line, right? Center line starts here, ends here, halfway, and in the quarter we got asymptote, right? Empty space there, empty space there. Okay. So this picture looks like, again, looks like this. Okay. Any points of two frowny eyebrows, right? Going asymptotic to the two vertical asymptotes that are placed at the first quarter, third quarter. The frowny mouth here, right? The sat mouth is right in the middle. You know what I'm saying, no? Okay, but being right around that. So I'm saying that this secant is being an even function in a sense that if we make a duplicate of that, you can just from right here, right? The y-axis is right there. So now with all that starts and see, there's another. Think about we'll take a mirror image of that and put it on the other side. See what I mean? Right. So that's starting. That ending point right here has a mirror image on this side right here, and then that halfway point is here. The starting point is exactly right on the same spot right there. Right? First quarter, third quarter, but on the mirror image. So we have another set of two vertical asymptotes, right? And the start point and end point. So think about it. See that frowny, those two frowny eyebrows. Gonna be just like that again. See what I'm saying, huh? And then that frowny mouth right here between the two is exactly right down there, right? And that's why this picture just now is really red. That is the exact mirror reflection of the ordinary frowny face, right? But right through the y-axis. And that's the reason why I can just now say, hey, secant here is an even function in general, right? Meaning, algebraically meaning when you put in a negative input, right, it comes out exactly the same output, right? With the positive input. See what I mean? Okay. So that's the idea. So that's for secant. Then on the other hand, cosecant, we just now looked at the graph. Right? Cosecant is indeed an odd function. So minus, putting in a negative angle, is going to be the negative cosecant, negative outputs of the ordinary function. This is the property of an odd function. And because just now I'm putting in the picture over here, y-axis, x-axis for our standard cosecant. So we got the vertical asymptote right here. You guys following? At start, center line is the x-axis. At the end, we got another vertical asymptote. Right? Start and we have a third vertical asymptote right at halfway. And then empty space, and these I put in dotted lines indicating that we don't always have to show these things, right? But it will always be there when we put the graph together. Let's see. So now here's how I'm seeing it. First quarter, third quarter, right? So first point right here, asymptotic cups, here asymptotic cups, right? Right down there. But make sure to be away from that empty space. Right? But now when you drew a duplicate of this guy and put that on the other side of here, here's how the picture looks. Okay? So you think about another period down here, right, on the negative side right here. Ending point, halfway point. Sounds good. Right. We've got the vertical asymptotes here. Another vertical asymptote here, right? And then that other vertical asymptote coincides with this one right on the y-axis. Quarter point, right? But this time right here, think about it, if we duplicate that from this one right here and this quarter point, we have a picture like this. That first cup happens right here, right? And then the other cup happens down here. And so now you're putting it together, isn't it? This cup is the exact mirror image of the black cup right here, but right through the origin, right? That's graphically, it points out that the graph order, the cosecant function is an odd symmetry. See what I mean? Right. So every point here has a point there on the graph, right? Like this, opposites, but only through the origins, right? That's the property about the odd symmetry. Yeah. Sounds good. So keep that in mind, and I gotta point that out so that we can later on utilize this valuable information into doing some good work with our secant and then cosecant graph. I purposely have you guys nail down the shape of the secant graph and the picture in your mind, the picture of this cosecant graph. So now we're going to push that into a certain example here. And every experience you have learned from the previous lecture is going to get carried in here. Let's call that example 3, because we're still in that big topic talking about the graphs of those other trig functions aside from the sinusoidal graph. Right? So let's look at example 3 right here. We want to sketch, get you guys comfortable with this skill right here. We want to sketch the graph. I'm going to show this as an example. We're all going to work with that together. So with this one right here, now algebraically, well, how about I'm going to leave some space and I'm going to fill it in later on. But we always going to need secant, cosecant, tangent, cotangent, or whatever, right? Sine, cosine, they're always going to have, we've gone this far right here, they're always going to have a center line, right? So for secant, there is a center line as a major feature, right? But the center line this time is going to be found as following: y equals -1. Write it down so that you guys can learn from the experience here. -1. Right. So -1 indeed. The reason we have that because it came out from right here. Well, I'm setting up. Right. So if it, think about it, if it's a +1 in some other problem, yeah, right, then the center line is going to be y equals 1 plus 1. Or if it's a +0.5 here, then it's y equals +0.5. Okay, so that last constant term again that we added to our secant or our trig function, that's responsible for the center line. And then eventually the picture is going to get busy, so later on I'm going to have to erase some of the minor stuff right here. And then the next thing, but for secant, keep in mind another major feature is that instead of talking about the amplitude, it doesn't have amplitude, right? But instead it's having empty space. See what I'm saying? The amount of empty space that see, there's a after the center line right here, right? After where you put the center line, and think about it. We can also start sketching it down at the same time right here. This is the x-axis. You can call that scale -1 right here. That's your center line. See what I mean? So the graph will happen around us, right? Okay. But the empty space is some amount of space that's being around the center line. So from your center line right here, up and down, there's an equal empty space, right? Swinging away. So empty space in this case, I will see that to be, the empty space here is a 1/2 up and down, right? 1/2 up and down. Up and down, right? From our center line. How do I determine that? It came from, so I should have written this in red ink right here. Right? It's a 1/2. Up and down, but that came out from, see, what you do here is you take the absolute value, right? Absolute value of 1/2, the coefficient. That coefficient in front of your secant function. See what I mean? That's the side that determines the amount of vertical empty space, right, around your center line. And then the period. So the period for your secant function. Okay. In this case, I'm seeing that as 2 pi, but over 3 here. Okay. It's 2 pi over 3. That's the period for this particular function. So how do I know that? The way how I'm seeing that is that. So hold on to your note taking right here. I want you guys to follow with my explanation, and then you have those time to take your note. You see, the reason I arrive at that 2 pi over 3, that simply was I go with any secant. The period is always 2 pi, right? The standard period for secant. Remember that from the ordinary one. And then this function right here is the same as we can always remember that trick. We always inside of our trig function we can always factor out that coefficient, right? That coefficient in front of our x inside of the secant. So now it's turning to a 3, and then factoring the 3 out, including the signs, we're looking at x, right? Minus, but now it's a pi over 6. Okay? And so that 3 is responsible for the period. Okay? If we divide that by the truth is absolute value of 3. Okay? And that's why I put that 3 here earlier, but really it came out from the absolute value sign of that. After you factored out that coefficient with the sign. Okay? So that's how we get that. That's how we get that 3 again. Now continuing with some further information, right? We got the start of our graph here. This value, after we factor out the coefficient in front of the x, right? This final value right here decides for us. And then it's already in the subtraction form like that, right? So the pi over 6 is going to be our starting point. Okay, so the starting point is at x equals pi over 6, right? And that comes right out from this number. Okay. And I got that minus 1 right here. All right, so now the ending point comes out easily. The end of the one basic unit is happening at x equals, right? Start at pi over 6. We're adding 2 pi over 3 here. You guys see what I'm doing there? It's always a start plus a period, right? That's making it. So now 2 pi over 3 here is the same as a 4 over 6, right? So making it all together a 5 pi over 6, right? That's our end point there. See what I mean? Right. So now we are about to make our way here. So in order to draw our graph, let's put down a starting point. Pi over 6. Your choice on the scaling. Pi over 6. That's the space. So pi over 6 is here, and that's whatever the space from 0 out to pi over 6, right? So that big of the distance is called 1 pi over 6. You guys follow it? So we got our starting point. So we placed down that starting point right here on the center line. So how I'm doing that there. But now the ending point, you see, I decided that this big of a space right here, of the physical space horizontally, is 1 pi over 6, right? So I'm going to go one more space like that. That's 2 pi over 6, 3 pi over 6, right? 4 pi over 6, and 5 pi over 6. See, these are all equal distance. You see what I'm saying now? So 5 pi over 6 is right about there. That's how we see that visually. We put it down on the center line, right? That's the ending point. And that's the starting point of our graph. And then the empty space is only a 1/2, right? It's only a 1/2 up and down from the center line. So center line is here, empty space is going to go like this, see, 1/2 away. So the scale here is 1, right? So 1/2 vertically is about that much. You guys agree on that, okay? Okay. So I'm going to put in the horizontal line to define the empty space. Right? Just like that. So now here's how it looks. Halfway we got the first quarter, third quarter on the center line, right? And the halfway we got. So first quarter we have a vertical asymptote. Third quarter we have another vertical asymptote. Okay. First quarter, third quarter is where it has a vertical asymptote. And now the first, see that frowny eyebrow It's starting right at the starting point, right? And this time the graph is swinging up because you see even in this final revised version, and after see positive input inside and and the coefficient in front of your secant function is positive 1/2, right? So there's no flips or whatever. It's just the ordinary shape. So now that means what the frowny eyebrow is going to go like this, rising up asymptotically, right, to your vertical asymptote. And then the same with your at the end, right, on the end of our center line, but right on that empty space line right there, we got another frowny eyebrow right there. Right now, see halfway, right on that line, right? It's that frowny mouth here. See what I mean? So center line is right at -1, right? Up and down about a half space away, we got that empty space, and the graph will never interfere in. And then see the graph appears outside of that empty space. That's how we draw it. And now we can start putting in the label over here. 1 pi over 6, 2 pi over 6, 3 pi over 6, right? Making it the pi over 2, so halfway is right at pi over 2 on our x-axis. Okay. And then these pointer here. 2 pi over 6, making it a pi over 3 right here at the at the first quarter and third quarter at that point, right? What's that value here? 1, 2, 3, 4, right? So it's making it 2 pi over 3. And then here I intended to go for just only one period, right? But we can just technically take this idea and keep building more basic units with that. So here, let me emphasize this for one period. That one period now. Then be ready that we may need to replicate that for more periods. All right. So now let's try another one for you. You want to sketch the graph. This given function. Cosecant in general. It's 2 times cosecant of all that minus 3x minus pi inside of the parentheses, the minus 1. Let's recognize what's easy with it. So the major feature, right? The main feature of our cosecant. There's a center line. There's other one. That we can do this for quite some time. Right? The center line. So what's the center line here? It's going to be y equals right? -1. So very similar arguments like the earlier problem that we've done. The last constant term right, after the Trig function right there, besides the center line right here, that's the decision for this center line at the y equals -1. Then cosecant also has a empty space, right? The amount of space that vertically swings away from that center line that what we found it. Empty space. This time my empty space here is VA 2 up and 2 spaces down, right, from the center line. So say the center line is here, 2 spaces up, 2 spaces down, you got an empty space again, right? And graph stays outside of that empty space. That's the idea. But for now, that's just some description. Later on, we're going to put all of that all together. And then the way how I got that empty space, once again, what I did was I took the absolute value of 2. Right? That came from this 2 right here, came from our coefficient in front of a cosecant function. Let me finish sketching out the equation right here, and then we're going to wrap up the sketch next time. So the periods here, now recognizing the period, it's a little bit of work, but the best way here is for this function. Let's go ahead and the inside part, so 2 cosecant with the inside of our cosecant function. There's a coefficient including a sign right in front of the x. Factor it out to make it -3, right? And then we have now, after factoring out that -3 right here, it becomes x, right, plus right? Pi over 3, guys follow it? And then minus 1, okay? And then this plus pi over 3 is the same as, is not as minus a negative pi over 3. So we're going to utilize that information a little bit later. So now with this negative 3 right here, we're looking at the periods being 2 pi, right? Standard, we're dividing that by the absolute value of negative 3. That's making it another 2 pi over 3 periods around window. Okay. And then the starting point, right, for our graph happens at x equals, see, we wrote it as plus pi over 3 as a minus negative pi over 3. So it starts at the negative pi over 3 again. Negative pi over 3. And then the ending point now has to be, of course, x equals, right, negative pi over 3. So start, we added with the 2 pi over 3. Right? Making it positive pi over 3. We have all of that information and ready to get the graph. Okay, so now let's put all of that information. Right? We sketch down, these are the major features of our cosecant graph. There's the center line, there's the empty space, right? And then the period here is being 2 pi over 3, the total window for your curve right there. And then there's the starts at the minus pi over 3. You got the start, now you got the end point now. So let's now put it in the picture over here. Now, I got to remind you before we even put that into further graphing, but so I mentioned in the earlier lecture that cosecant, right, is an odd function. So when you take the negative input, right, it's going to be the same as minus cosecant of the ordinary positive input again. So I'm bringing this in so that I can use this property being an odd function, so that our equation here, y equals 2 cosecant minus 3, see that negative input right there? X plus pi over 3 after factor out the linear expression inside, we can see that with this, it's cosecant of a negative input, so we can turn that into minus, see the negative sign can be brought out front, making it minus 2 cosecant, right? And then here I'm looking at now 3 times the negative sign got brought into the front coefficient in front of your cosecant function. And now here we have x plus pi over 3, right? Parentheses minus 1. So with this final form right here, we are very ready to get the graph down. Every information remains exactly the same. And here you can see that the empty space is still 2, because in the end, even if it got a negative sign right here, it's still going to be the empty space is the absolute value sign. I should have put that in absolute value, because absolute value is the same as absolute value minus 2 as well. Okay. So now on this board, here, that other board, I don't have enough space, so here on this board, let's draw the picture over here. So that's the x-axis. The center line, so we make our scale right here. The center line is down at negative 1. So negative 1 is here, that's the center line, right? We've got the center line parallel with the x-axis, right? Y equals negative 1. That's our center line of the graph there. Okay, and then there's negative 2, negative 3, right? And then 0 and 1. Okay. So they are the empty spaces being 2 vertical spaces up and down, right, from your center line. So that means the graph has to be above that point and below this point. Right, above that, out. So basically the graph has to be outside of that empty space. Okay. Right. And then for your, so center line is here. We're gonna make our starting point, right? So our starting point is at minus pi over 3. So we set our scale pi over 3. You can call that maybe that's a little too small. Okay. So you can make it about this big right here is a pi over 3. So minus pi over 3 is right here on the x-axis. Okay. So that means that's our starting point right on the center line. And so the feature of our cosecant graph is that center line is here. At the starting point, we have the first vertical asymptote, right? And then at the ending point of our basic units right there. We got another vertical asymptote, and right at halfway we have another vertical asymptote. And so right here at the starting point, we put a vertical asymptote here. Now minus pi over 3, and the graph is going to end, the basic units of our cosecant is going to end at this particular spot right here. It's about equal distance away from the y-axis, right in the middle. Right? So at that point right here, we got a positive pi over 3 after we numerically label that. And so right here, that's right on our center line, the graph will happen around that. Right? And then now with the center line in here, right, the right halfway, which is x equals 0, the y-axis, we have another vertical asymptote there. Right? So the graph, the total window, the total period window got broken up into two separate portions. All right, and so at the quarters, right? At the first quarter, the ordinary cosecant graph goes like this on the center line, right? But away from that empty space, so it goes like this. The peak of that bottom cup right there, right? The bottom part of that upper cup right here has to be right at the first quarter, and then at the third quarter, we got a cup, but right on the bottom line of the empty space, but pointing down. Right? That's the ordinary cosecant right there. But now our cosecant here has before I actually draw the actual graph, our cosecant at the final version, after we also apply the odd nature of the odd symmetry of that, then it looks like we can turn that into the -2, right? So the negative in front now is going to make our graph flip. So this graph right here is going to get actually flipped. So the version we actually want now this time is going to be kind of like this. Right? Center line, right? Empty space. The start is right here, the end is right here. Some start, some end, right? Halfway, vertical asymptote. But then the first quarter right here, the cup this time is going to point down. See what I'm saying? No? Right? And at the third quarter, that's the shape of our picture. Third quarter, the cup is going to end up. It's going to be pointing up, as opposed to as being opposite to that original version. So we're going to actually take the shape right here, we bring that right into our picture. So starting point, ending point, halfway, quarters. So quarters have to be at negative pi over 6 right here, right? And then it drops right on the center line. You guys with me there? Quarter, right? And then another pi over 6 right here. Right? That's the second quarter. The third quarter, halfway point. So the graph looks like this. So this is where the center line is. The empty space is down here, right? So that's why it's important that you draw the empty space right here. The graph goes like this. You guys can that, okay? Right. And then at the third quarter, right? At the third quarter, we got another cup, but this time the cup is pointing up and being asymptotic to the two vertical, in between the two vertical asymptotes. Okay? That's how we completed our graph. The center line for our graph is right here, which is important to nail it down. The x-axis is actually right there, right? And we got the vertical axis